Hi, everyone. This is the lecture for Friday, September 27th for Stat 230, Section 1, and it's lecture 11 if you're counting. So recall from last time we had the idea of a random variable, which is a function that takes points in our sample space and maps them to real numbers, but it doesn't have to satisfy any of those axioms of probability. So you could have negative values, you could have values bigger than 1. All of the only requirements is that it has to be a function. So each sample point can only map to one number. But multiple sample points could map to the same number. It doesn't have to be a one-to-one function or anything like that, just a function. And then we had the difference between discrete and continuous random variables. For now, we'll be focusing on discrete, which means there's a countable number of values that the random variable maps to. And so it's mapping to it. That means it's the range rather than the domain. So the range of the random variable is the possible values the variable can take on. Then we had this idea of the probability function. This probability function, little f of x, is the probability that the random variable, capital X, takes on the value little x. So it's just the probability that x equals little x, and it's defined for all x in the range of the random variable. So today we're going to talk about the CDF, which is another function that defines how a random variable behaves. CDF stands for cumulative distribution function, but I'm too lazy to write that out, so CDF it is. And then we'll talk briefly about the first 3 of the named distributions in the course. There are 6 discrete named distributions. We'll just briefly touch on 3 of them today. The uniform, which is very simple, the hypergeometric, and the binomial. And the hypergeometric and binomial are very similar to each other in a key way. So that'll be it for today. So next I want to define the cumulative distribution function. Again, due to laziness, the CDF of a random variable x is defined as follows. We call it capital F of small x. So the f is capital, but the x is still small, and that matters. What the cumulative distribution function does is it tells us the probability that x, the random variable, capital X, is less than or equal to little x. So it's basically saying the random variable takes on a value, any value that's less than or equal to the value little x. So we can think about the relationship between the cumulative distribution function and the probability function by thinking about stacking these probability function values on top of each other, right? If we have a random variable like we did last time, where we had x can take the values 0, 1, 2, or 3, and the probability that it did so, you can review this if you don't remember, this is a lowercase f here, the probability that it did so was 125 over 216. For 1, it was 75 over 216. For 2, it was 15 over 216. And for 3, it was 1 over 216. So we calculated those at the end of last class. If we have this probability function, then we could think about what does our cumulative distribution function, capital F of x, look like at those points. Well, if we want big F of 0, that means x takes on a value that's less than or equal to 0. Well, the only way to do that is to be 0. There's no negative values for this random variable. Variables could be negative, but this one isn't. So the probability of being less than or equal to 0 is just the same as being equal to 0. So we have 125 over 216. But then it gets more interesting. If we want big F of 1, that means the probability that x is less than or equal to 1. In other words, the random variable takes on the value that is less than or equal to 1. It could be 0 or it could be 1. And with or, remember, we use the addition rule, and those are mutually exclusive, so we can just add them up. So the probability that x is equal to 0 or 1, in other words, less than or equal to 1, is going to be the sum of these two components, right? 125 plus 75, that's 200 over 216. We can build up from there. So the probability x is less than or equal to 2 is adding up 0, 1, or 2. So we add up those 3, we'll get 215 over 216. And then finally, at the end, what we'll get, maybe not surprisingly, is 1. Right? If we add up all of the possibilities, we'll end up with 1. And that makes sense. The probability that a random variable takes on any value less than or equal to its maximum, for sure that's 1. It's got to take a value less than or equal to its maximum if it has a maximum, because it must equal exactly one of its values. So we have this cool relationship here between big F and little f. And then we can also graph this. This is kind of interesting. So this function, the CDF of this random variable x, is defined this way, and it's defined for all real values of x. So not just defined on the points in the range of the random variable, but it's defined for all real x, which means we could graph it on a regular graph. So let's try and do that. Let's squeeze a graph on here. Here's my x-axis is going to be x, and my y-axis is going to be big F of x. And the only thing we have right now are 4 points. We have the point at 0, it's equal to 125 over 216. So let's say that's here-ish, just making this up. At 1, the value is equal to 200 over 216, so it's a bit higher. It's up here, maybe, like that. At 2, it's a little bit higher than that. There we go. And then at 3, it's ever so slightly higher than that, just like there. So it's not perfectly to scale. But that's all we have. We have 4 points, but we really want big F of x to be defined for the entire real line. So what we have to do is think about what value will big F of x take when x is not an integer. It's kind of interesting. First of all, we can think about what happens when x is negative. If x is negative, there's no way that the random variable is going to be less than or equal to something negative, because this variable, the lowest possible value, is 0. So we can think about this x-axis here extending in this direction, and there's a line here going that way. So the value is equal to 0 for all negative values. But then at the point 0, there's a discontinuity. It jumps up because this is the value of big F of 0. So we can imagine there's like a little empty circle here. Oh, that looks pretty good. It jumps up. There's a discontinuity in the graph there. All right, that's cool. What about anything bigger than 3? If x is bigger than 3, then we're asking what's the probability that this random variable x takes on a value that's less than or equal to something bigger than its maximum value? Well, that's guaranteed for sure. So we can think about this line once we get here staying at the value 1 and being flat forever. So this value here is the value 1. So it starts at 0, 0 for a while back in all the negative values. Once it gets to 1, it stays there forever. And then what happens in between these other values? Well, let's think about it logically. Let's imagine we want the value at 0.5. What's the probability of getting less than or equal to 0.5 for this random variable? So we know it can be 0, 1, 2, or 3. If we want something that's less than or equal to 0.5, the only option is 0. It can't be 1 yet because 1 is not less than or equal to 0.5. And that's true actually for any number in between 0 and 1. For any number between 0 and 1, the probability of being less than or equal to it is just the probability of being 0. So really what happens once we get to this point here, it goes flat for a while until we get to 1, and then again we have a discontinuity. It jumps up. So there's an open circle here, and it jumps up to there. And then the same thing will happen. This one will stay flat for a while. Oops, sorry, not very flat. This one will stay flat for a while, and then there'll be a discontinuity. It'll jump up, and then this one will be flat for a while, and then jump up. So you can see we end up with this step function. It's kind of like a staircase of values for this cumulative distribution function. And it looks kind of neat. The cool thing about it is, of course, the size of these jumps, the size of the height of that jump, the height of that discontinuity, that's little f of 0. And the height of this discontinuity is little f of 1, etc. So you can think about the relationship between big F and little f. Big F is the little f's kind of stacked on top of each other. And little f is the sizes of the jumps in big F. So if you have one of the functions, you can automatically get the other one. Each one contains the full information about the other one. Kind of cool. All right, I'm going to erase the board and talk about some general properties of cumulative distribution functions. So I'm going to pause the video while I erase. Okay, magic. So some properties of this cumulative distribution function, big F of x. It has 4 interesting properties, one of which is that it's non-negative as well. So big F of x is always non-negative. The reason for that, we can be pretty obvious about that. That's because we know it's a probability, right? It's a probability, and so it must be non-negative by the axiom 1 of probabilities. Number 2 is that it's going to be right continuous. So it's a right continuous function, and it looks like a step function. So that's kind of neat. So that's not actually a formal property. That's just how it looks in terms of a discrete random variable. Another thing is that it's going to be non-decreasing. So remember, that's not the same as increasing. So that just means the value can stay the same for a while, but it can't ever go down. So it can be flat or it can go up. And the reason for that is kind of more interesting. You think about two different values, say x and y. If y is bigger than x, then the probability of the variable being less than or equal to y contains the event that the variable is less than or equal to x. It's for sure, if it's less than or equal to x, it's definitely less than or equal to y, but not the other way around. So I think I said it backwards. If a value is less than or equal to 3, then it's obviously also less than or equal to 4. So that means anytime we increase the value of the argument of the function, we're capturing more and more possibilities, more and more probabilities. So you can never lose probability by expanding the values that the variable can take on, essentially. So that's an interesting function fact as well. The next is that the limit as we approach negative infinity is going to be 0. So I'll write this formally. The limit as x approaches negative infinity of big F of x is equal to 0. And again, that should be fairly logical. If we're getting this value smaller and smaller and smaller, we're saying the probability that the variable is less than or equal to something that's going that way, all the way to negative infinity, that probability is going to go down to 0. And similarly, the limit as x goes to positive infinity of big F of x is equal to 1. Because even if the variable has no maximum, there are variables that have just countably infinite but no maximum value. If we expand that and we let x go all the way towards infinity, eventually we're going to capture all of the possibilities for what the random variable can equal. So that probability has to equal 1. So we have a non-decreasing function which has a limit of 0 when we go to negative infinity and 1 as we go to positive infinity. That's what all our functions will look like. And in the case of a discrete random variable, it's going to be a right continuous step function. So it's going to look like stairs, and all of the discontinuities are going to be left discontinuities. So the value of the function at a point is always equal to the limit from the right, but not necessarily from the left. Okay, I'm going to pause again, and we'll talk about the first of 3 distributions. All right, so the uniform random variable is probably the simplest random variable, other than maybe a constant. That's kind of a silly random variable. And essentially with the uniform random variable, you have a number of different possible values that the random variable can take on, and they're all equally likely. So it's got a uniform, even distribution, like you're making a nice cake and you spread the frosting so it's exactly even. That's what a uniform random variable looks like. So formally, we define it, a random variable x that takes on values, say, between a and b inclusive. So we'll call them a plus 1, a plus 2, etc., up to b, where each value is equally likely. That's what we call a uniform, or rather a discrete uniform random variable. Usually we specifically refer to that as a discrete uniform. Sorry for squeezing that on there, discrete uniform random variable. There's a continuous version as well, spoiler alert. So the idea with this discrete uniform random variable, notation-wise, you might see this written like this. X follows a discrete uniform random variable on A, B. I use square brackets there because we want to include both endpoints. So for example, if you roll a fair 6-sided die and X is the number that shows up, then X would be discrete uniform on 1, 6 with square brackets. So the cool thing about the discrete uniform random variable is that it's really easy to determine what its probability function is. Let's find the probability function. Well, we know that all of the values of this random variable are equally likely, which means that this probability function, f of x, must be a constant. It can't depend on the value because it has to be equal. So let's call it a constant c, for x equals a plus 1, a plus 2, etc. up to b. For x equals a up to b. So it has to be a constant because of the way we've defined it. We've defined it to be equally likely for all of its values. And so we need to use the properties of probability functions to be able to figure out what that constant is. So we know that we need the sum of the probability function over all of its values from x equals a up to b inclusive. We need that sum to be 1. That's one of the properties of probability functions. So we need this to equal 1. And so, since every single one of these is the same, it's just a constant added up a certain number of times, essentially we want the number of terms in this sum times c to equal 1. So in other words, c is just 1 divided by the number of terms in the sum. So then how many is that? Well, if we're going from a up to b, your first instinct might be that there are b minus a terms in the sum, but that's not quite right. There's going to be b minus a plus 1 terms in that sum. And if you don't believe me, check it with a discrete uniform 1, 6. Right? If we're going from 1 to 6, there's 6 possible numbers, 6 minus 1 plus 1, because we're counting both endpoints. So there's, just add a note here, there's b minus a plus 1 terms in that sum. And so the only possible value for c that gives this, makes this probability function a valid probability function and makes it add up to 1 is that f of x, the constant, is 1 over b minus a plus 1. I'm sorry for that looking weird. There we go, b minus a plus 1. So the uniform distribution is just a constant for those values, and the value that we need to make the total add up to 1 is b minus a plus 1, or 1 over b minus a plus 1. I could graph that, do that over here. Remember with a discrete random variable, we can't use a regular graph, we have to use a histogram. So here's, let's say, a is in here, and a plus 1 is here, etc. And here's b. The discrete uniform random variable histogram is going to look like this. Pretty boring. Looks like a cake that's been smoothed out nice and smooth. The height of this line here is 1 over b minus a plus 1. And these sort of, each column, you can think about that as being of width 1. And so the area of that rectangle is 1. Kind of neat. So that's what the probability function of the discrete uniform random variable looks like. I'm going to pause again and erase, and then we'll talk about its cumulative distribution function. Okay, so to find the CDF of this discrete uniform random variable, we have to think about the relationship between the probability function and the cumulative distribution function. So I kind of alluded to it before, but maybe a little bit more formally in general, if we want f of x, big F of x, we know if x, of course, is equal to a value in the range of the random variable, we can take it by stacking up the sums of all of the other smaller values of the probability function. So it'll be little f of 0 plus little f of 1, plus little f of x. So that's how we can sort of get the relationship between big F and little f. It's interesting to get the reverse, actually, as well. Similarly, if we wanted to, we could find little f from big F as the size of those jumps, the size of those discontinuities. So if we think about that graph before, we want the difference in heights of the line big F of x at one value and the value right before it. So this would be big F of x minus big F of x minus 1. And this is all assuming we have sort of an integer valued random variable. Of course, we could have non-integer values and then this breaks down. But pretty much all the variables we're going to be dealing with have integer values. So this is kind of neat. We can get the CDF by stacking up the PFs, and we can get the PF by taking the difference in two adjacent values of the CDF. So back to our uniform random variable, where x is a discrete uniform on AB. If we want big F of x, we need to think about 3 cases. First of all, if x is less than a, less than the smallest value that the random variable can take on, for sure we know it's 0. So it's going to be 0 if x less than A, strictly less than A. Because there's no way a uniform random variable whose smallest value is A, there's no way that variable can be less than anything strictly less than or equal to anything strictly less than A. Can't happen. And similarly on the other end, once we get to B, then for sure the variable is going to be less than or equal to its maximum value. So it's going to equal 1 if x is greater than or equal to B. So the only thing we really need to focus on for this cumulative distribution function is what happens in between. So we had our probability function here as being the constant 1 over b minus a plus 1. And so what we want is big F of x, just a little side note here, it's going to be the sum as, let's call it, need a dummy variable, let's call it u, going from the lowest possible value a up to x of little f of u, right? We're just going to, again, using a dummy random variable, sum up all of the values from the smallest one up to and including x, and then add up those values. Well, each one of these is just 1 over b minus a plus 1. So the only thing we need to know, again, is how many terms are in this sum. Again, assuming x is an integer, then there's going to be x minus a plus 1 terms in the sum. X minus a plus 1 terms. And each one of these is equal to 1 over b minus a plus 1. So when we put it all together, we just get x minus a plus 1 over b minus a plus 1. That's it. So we'll put that in here. X minus a plus 1 over b minus a plus 1 for anywhere x between a and b. This isn't quite right yet, though, because I said this was assuming x was an integer. What if x is not an integer? Then essentially all we have to do is chop off the decimal place. So round it down to the next, to the smallest integer, and then we can do this calculation. So remember, it looks like a sort of staircase, like a step function. So what we really want, if you've seen this notation before, it's called the floor. We want the floor of x. In other words, the integer part of x. So if x is an integer, great, leave it alone. If x is not an integer, chop off the decimal place and then do this calculation. So now we've defined big F of x for all real values of x. Remember, the definition is not complete unless you specify it for all real values of x. So here we have it for the discrete uniform random variable. And what does this look like? Let's graph this one. It's really pretty, actually. So imagine here's A, and here's B, and here's A plus 1 for good measure. So we know that below A, it's 0. So it's going to be 0 for this whole line. And then at A, it jumps up by 1 unit of B minus A plus 1. So it'll jump up, say, to here. And then it'll be flat until it gets to A plus 1. And then it'll jump up again to 2 over B minus A plus 1. And then it'll be flat for 1 unit, and then it'll jump up again. So we end up with this beautiful, perfectly rising staircase. And then eventually, when we get to B, it'll equal 1, and then it'll stay there forever. Stay at 1 forever. So the function looks really nice. It's a nice little step function where all the jumps are of size 1 over b minus a plus 1, and all of these widths are 1 unit as well. So that is the discrete uniform random variable. In terms of examples, I mentioned that the roll on a fair die is a great example. Another one would be the location of an item that you're looking for in a list, or any object. If you have a linked list or a bunch of balls in an urn, whatever, or a bunch of keys on a ring, if you're going to look through it until you find something, then the position of the thing you're looking for is equally likely to be anywhere. So you could think about the number of tries it takes to get the item that you want. If it's randomly somewhere in this list, that's going to be a uniform random variable. So a discrete uniform random variable is a useful tool to build other random variables from. All right, that's everything for the discrete uniform random variable. Next, we're going to talk about the hypergeometric. So give me a sec, I'll pause again and erase. All right, So we have next the hypergeometric, which is the longest name of all the variables. The hypergeometric random variable is based on a scenario that we've talked about a lot in chapter 3 kind of stuff, where we're selecting objects without replacement. So the setup is pretty involved. I want to talk through it. Suppose we have capital N objects. And these objects are split into two types, two categories. We have R successes, and then of course N minus R we're going to call failures. N minus R failures. They don't have to literally be successes and failures, but they could be any two types. So I mean, if we have a bunch of objects and or let's see, a bunch of dice rolls, and we call a success. That's a bad example. Sorry, I'll think of something better. Okay, but a bunch of cards in a deck. We call a success a face card, so king, queen, jack, or ace, and we call a failure any other card. So as long as we have the ability to sort of classify the objects into two types, then we can work with this hypergeometric random variable. Dice rolls was a bad idea, just ignore that one. So cards would be a great example. So those are the objects that we have, and we know the classification of each one, and we know how many of each there are. There's R successes, that's a lowercase r, and then capital N minus R failures. Then we're going to select lowercase n of these capital N objects without replacement. Select little n objects without replacement. And then that's why dice was a bad idea, because you could get the same number twice. But we're going to do this. We're going to select n objects without replacement and let x, the random variable, equal the number of the objects that we select that are successes. The number of successes we get. So again, from returning to that card example, if we draw 5 cards from a deck of 52 and we let x equal the number of face cards that we get, then x would be a hypergeometric random variable. The hypergeometric random variable takes 3 parameters. So notation-wise, we say x follows a hypergeometric. I just use hype for short because I'm lazy. And we need to specify all 3 parameters. Capital N, the total number of objects, R, the number of successes, which we know in advance, and the number that we are selecting. So we need 3 parameters to specify the distribution of a hypergeometric random variable. So we can think about, if we know those 3 numbers, that defines the distribution. Another interesting example, actually, of a hypergeometric would be the lottery. We talked about this back in chapter 3. So if we think about x being the number of winning numbers on our Lotto 649 ticket, then that would follow a hypergeometric distribution. So the number of winning numbers on a Lotto 649 ticket, it's going to be hypergeometric because the total number of objects are the numbers between 1 and 49. So there's 49, capital N is 49. R, we're going to define a success here to be one of those winning numbers. And we know how many winning numbers there are. There are 6 winning numbers. And then little n is the number that we select. So the number of numbers on our ticket. In this case, that also happens to be 6. So that would be an example of a hypergeometric random variable with parameters 49, 6, and 6. X is the number of winning numbers on our ticket. Obviously, we could have 0, 1, 2, 3, 4, 5, or 6. And 6 is really, really unlikely, so don't play the lottery. It's a terrible waste of money. So that's the idea with the hypergeometric distribution. The keys are that we know the classifications ahead of time, and there's a fixed number of objects, and that we're selecting without replacement. Those are 2 very important things with the hypergeometric random variable. And then if we're doing that, and we're counting up the number of successes that we obtain, that makes it a hypergeometric random variable. All right, next we'll talk about the probability function in the range. Just give me a sec to erase. Okay, so we want to find the probability function for the hypergeometric random variable. So that's going to be little f of x. And remember by definition, that's the probability that the random variable x takes on the value little x. So in the case of this hypergeometric random variable, that we can express that in words, what that means. This means the probability that we select exactly x, lowercase x, successes when we do this selection. So we get x successes when we do this selection. But if we get exactly x successes, that also tells us how many fails we need as well, because we're selecting little n objects. So by necessity, if we want x successes, the rest of them have to be failures. So it's not just this. If we want x to equal x, big X to equal little x, we need to select little x successes and the rest of them, n minus x, fails. So that's what we're saying here. If we want the random variable to equal x, we need little x successes and little n minus little x failures. And that is just a chapter 3 problem. You think about using the classical definition. How many ways are there for our denominator to select little n objects from big N objects without replacement, where we don't care about the order? That's right. I know you said it. Big N choose little n. That's how many ways there are to select these objects. And then we want to say for our numerator, how many ways are there to satisfy this exact condition, that we get exactly little x of the r successes and so we multiply exactly n minus x from the big N minus r failures. So we need both of those things to happen. So we're going to multiply two things together on the numerator here. Then we need from the r available successes, we need to select x of them, and multiply from the capital N minus r failures that are in existence, we need to select little n minus x of them. So that is the probability function for the hypergeometric. And here's a really good way to remember it. This is how I always remember it. The two numbers in the tops of the chooses on the numerator have to equal this one here, and the two numbers on the bottom of the chooses have to equal this one here. That's how I remember the probability function of a hypergeometric. Because again, we need to specify exactly what type each of those objects that we're selecting is. And we know that we have to get, we're partitioning the object pool into two categories, R successes and capital N minus R failures. So we want exactly X of the successes and exactly N minus X of the failures. And then we're just multiplying those together in the middle. Make sense? All right. So then what about the range? A probability function is not complete unless you also specify the range, because we need to know which values it takes this on. So the range of the hypergeometric is a little bit weird, actually. Obviously, for the range, the value x can't possibly be less than 0, right? So x for sure is going to be greater than or equal to 0. The worst we can possibly do is get no successes in our selection. And similarly, the best that we can possibly do is get all successes, right? We're selecting little n objects. If we get them all to be successes, fantastic. We can't go higher than that because we're only selecting n objects. But there's other restrictions as well. What if we were selecting 5 cards from a deck of 52 and a success was an ace? There's only 4 aces in the deck. So no matter how hard we try, we're never going to get more than 4. So x not only has to be less than or equal to n, but it also has to be less than or equal to the number of available successes. And that's required because we are selecting without replacement. Sorry, that's an R. It looks a little bit weird. There we go. So x has to be less than or equal to the number of objects that we're selecting, but it also has to be less than or equal to the number of available successes that there are to select. We could run out of successes if r is smaller than little n. Same thing on the negative side too, or on the lower end of the range. It might be possible to run out of failures if if n minus x, if n minus r is really small. So if there's lots of successes out there, we might run out of failures to get. So there's also a minimum that is going to have to be bigger than or equal to the difference between the number that we select and the number of failures available. So I guess n minus r. That makes sense. So this is the total number of failures available, and this is the number of objects that we're selecting. So the number of successes we get will be at least as big as the number of objects we select minus getting all the failures that could possibly be gotten. Again, because we're selecting without replacement, it's possible to run out of successes or to run out of failures. Now, obviously, this might be negative, and if it is, then this lower bound will apply. But if this is non-negative, then this is the lower bound. And then similarly for the top, right? If this is bigger, then this is the upper bound that applies. If this is bigger, then this is the upper bound that applies. So the range is kind of weird because we have to satisfy two sets of conditions at once. I want to do a quick example with the hypergeometric, and then we'll move to the binomial, and that'll be it. Give me a sec. Okay. So for this example, let's imagine that you're playing a card game where you start with 10 cards in your deck. So this is like a deck building game, like maybe Dominion, or actually there's a really fantastic game called Harry Potter Hogwarts Battle that my kids are really into with me, and it's the same idea. You start with a deck of 10 cards, and eventually you can buy more cards, but you start with just 10. And out of these cards, 7 of them will give you money, with which you can buy more cards, and 3 of them are useless. Well, they're not useless, they're not good right now at the start of the game. So there's 7 money cards and 3 non-money cards. So when you start the game, you shuffle your deck and you draw 5 cards. And then your hand obviously is going to contain a certain amount of money. It might have 5 money cards and you can buy a really good card. It might have 4, it might have 3. We want to think about letting X equal the number of money cards in your opening hand because that'll determine how your game will progress. So we're going to let X equal the number of money cards in your hand. In Harry Potter Hogwarts Battle, the money cards are called Alohamoras. So my kids are always running around going, Alohomora! It's really cute. Anyway, so this is how this works. We're going to figure out what distribution this is. Let's check that it satisfies the definition. We have a fixed number of cards. So that's our capital N. We know how many are successes and how many are not. And we're drawing 5 cards without replacement. Obviously, I don't need to say that. If you're drawing a hand of 5 cards, that means you're drawing without replacement and you don't care about the order. And we're counting up the number that are successes. So that's great. That means this satisfies the conditions of the hypergeometric with the following parameters. Our capital N, I mentioned that before, that's our total population of objects. So that's our 10, capital N equals 10. Our lowercase r is the number of successes that are available to be had. So that's going to be 7, capital N, lowercase r. And then the number that we are selecting, lowercase n, that is going to be our 5. So the parameters always go in this order of capital N, R, and then lowercase n, and that looks like an X. Sorry, that's a 5. So our parameters are 10, 7, and 5. And that means, of course, that the probability function, f of x, for this particular random variable is going to be, well, we need to choose x of the 7 successes. So 7 choose x. We need to choose 5 minus x of the 10 minus 7 failures. So 3 choose 5 minus x. And then as a whole denominator, that's going to be out of the total number of ways to draw this opening hand. Well, there's 10 cards and we're picking 5 of them. So there's 10 choose 5 ways to do that. So we could calculate this, for each possible value of x. But what are the possible values for x? Obviously, the maximum you could get, if you're drawing 5 cards, the maximum you could get here would be 5, right? You could get 5 money cards, you'd be happy, you could buy something really good, like, I can't remember, I think like Cedric Diggory is 5 coins or something, whatever. In Dominion, it's like the marketplace is 5 coins, whatever. So 5 is the maximum for sure. You could have 4, like 4 money cards and 1 non-money card. We could have 3 money cards and 2 non-money cards. We could have 2 money cards and 3 non-money cards, but we couldn't actually go lower than that. We couldn't have less than 2 money cards because we'd run out of non-money cards. The worst we can do, like the lowest opening hand you could get, is 2 money and 3 other things. So the range is actually just 2, 3, 4, 5 for this random variable. And if you want to double check, you can calculate this number, this expression, for each of those 4 values, 2, 3, 4, and 5, and they will indeed add up to 1. In fact, it's actually guaranteed that they'll add up to 1 because of what we call the hypergeometric identity when we were looking at section 4.6. So that's saying that the numerator here, if we sum these values up as x goes from 2 up to 5, those will guarantee to equal 10 choose 5, and thus the sum of this probability function will add up to 1 perfectly. So kind of neat. You can try that out. Think about the probability of getting 5, an opening hand with 5 money cards. It's actually reasonably likely, and it's less likely to get only 2 in an opening hand. And so that's good news if you play Harry Potter Hogwarts Battle or if you play Dominion. All right, so that's it for the hypergeometric. Next, I'm going to talk about the binomial, and that'll be it for today, just a little bit about the binomial. On Monday's class, we'll see how the hypergeometric and binomial are really linked to each other, and one can be used as an approximation for the other. But I want to introduce the idea of the binomial in today's class. Okay. So the binomial random variable is one of actually 3 different named distributions that rely on the same setup. So I'm going to talk a little bit about the setup for the binomial. It has a name. These are known as Bernoulli trials. So Bernoulli trials are named after, there were 2 mathematicians, brothers, both named Bernoulli, and I don't know which one of them was the one who came up with this, but there are two mathematicians. The Bernoulli trials are a series of trials, so like an experiment that you can repeat over and over with 3 conditions. In order for something or for a process to be considered Bernoulli trials, it needs to have these 3 properties. First of all, the trials have to be independent. So whatever happens on one trial can't influence what happens on the next trial. Bernoulli trials are independent. Second of all, on each trial, the outcome has to be classified into one of 2 types. So each outcome on each trial has to be either called a success or a failure. Again, these don't literally have to be success and failure. So you could do, like if you're spinning a roulette wheel, like success could be the number you bet on and failure could be anything else. Or success could be red and failure could be black or green, or whatever. Like however you want to classify them, you can define something as a success, and then anything other than that is defined as a failure. So there don't just have to be only 2 outcomes. It's just that whatever outcomes there are have to be classifiable into 2 types, either success or failure. And the third condition is that the probability of success can't change over time. We give that probability of success a name. The probability of success on any one trial we call lowercase p is constant. So if you're rolling a die over and over, it doesn't warm up or start melting in your hand or anything. Nobody's keeping score and trying to like adjust the probabilities on anything or tilt something. It's just a constant probability of success each trial, independently of everything that happened before, and each trial has 2 possible outcomes. So that's this idea of Bernoulli trials. And again, lots of things can be modeled with Bernoulli trials reasonably well. Independence may or may not hold in practice, and constant probability may or may not hold in practice, depending on your whatever the situation is. But those are the assumptions required for Bernoulli trials. So I think it's really important to understand the assumptions behind a model before you use it, because no model is perfect. Every model is a simplification. But if you're going to use a probability model to investigate something, it's good to know how well reality actually follows these assumptions. So I'll be asking a lot about that in class later times. So with this binomial random variable, we have this setup. We have these Bernoulli trials. There's a sequence of trials, independent. Each one has one of 2 possible outcomes, and the probability of success is constant. Then, for a binomial random variable, we're going to do little n trials. And we let x equal the number of successes we get. So you can already kind of see how this is a little bit similar to the hypergeometric. With the hypergeometric, we were selecting little n objects and then counting x as the number of successes we get. So this is kind of similar. We're doing n trials and letting x equal the number of successes we get. So there are similarities between the binomial and the hypergeometric. But with the binomial, the key is this idea right here, that the probabilities are independent, that the trials are independent. With the hypergeometric, that's not true. With hypergeometric, we're selecting without replacement. So if we get a success on the first trial, that means, or the first selection, that means the other selections are less likely to be a success. So the probability of whether the next object is a success or not will change based on what occurred earlier on. For the binomial, none of that matters. Every selection is completely independent of what happened before. So that means things are a lot simpler. The range of the random variable is now just 0 to n, because we could have all failures or all successes. There's no way to run out. It's as if we're selecting with replacement. So it's kind of, I'm going to write that down. It's similar to a hypergeometric if we selected with replacement. With replacement. So we'll have this binomial random variable able to capture this probability of success and the number of trials that we do. Obviously, both of those things will impact how the probability function turns out. And I just want to define the notation and quickly get our probability function, and then that'll be it for today. So one more slide. All right, so the notation for the binomial random variable, we say x follows the distribution, that sort of tilde means follows the distribution of binomial, bin for short, and then we need to specify, as I mentioned, those two parameters. So remember, the hypergeometric had three parameters, capital N, R, and little n. The binomial only needs two. It needs n, the number of trials that we're doing, and p, the probability of success on each trial. So let's find the range and probability function. The range is really easy, as I mentioned. The worst we could possibly do, let's say something simple, flipping a coin and heads is a success and tails is a failure. We flip a coin 10 times, the worst number of heads we could possibly get is 0. We can get unlucky, we could get all tails, 10 tails in a row. It's unlikely, but not impossible. So the lowest possible value is 0. Or we could get 1, 2, etc. And the best we could possibly do, the most heads we could get if we flip a coin 10 times, would be 10. So in general, up to n. So the range is very simple, 0 up to n. There's no possibility of running out of successes or running out of failures because the trials are independent. We could always get another success. Even if we just had 10 successes in a row, we could always get another one. So the range is relatively simple. And for the probability function, little f of x, we want to think about the same idea in terms of building this probability. We need to have x successes, which means we also need to have n minus x failures. That's still true. So we want the probability that we get x successes and n minus x failures. So think about the probability of that happening. We want to have a success, which has probability p, x times. And it has to happen multiple times. So we need to multiply those probabilities together. So you have p times p times p, etc., for each of those successes that we want. So the probability of the successes is going to be p to the power of x. And we also want n minus x failures. Well, if the probability of success is p, then the probability of failure is going to be 1 minus p. And we need n minus x of those. So we need 1 minus p times 1 minus p times 1 minus p, etc., n minus x times. And then we need 1 minus p to the n minus x. But if we just had this, that would be like saying we had to get them in that order. X successes in a row, and then n minus x failures in a row. But we don't care about the order. They could come in any order. We could have head, tail, 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 whatever. We could have it mixed up in various ways. So then we need to incorporate the number of ways that these objects can be arranged. In other words, we have x successes and n minus x failures, and we want to put them into an ordering where we can't tell the difference between the successes and we can't tell the difference between the failures. So when you think about the number of ways there are to do that, again, back to a chapter 3 problem. Thinking about if we have these positions, 1, 2, 3, whatever, n positions, and we want to fill them with X of these positions need to be filled with successes, and then automatically the rest of the positions will be filled with failures. So however you want to think about it, choosing the spots for the successes to go, or arranging these objects where we have n objects in total, x of which are successes and n minus x of which are failures. The number of ways to arrange those objects is n choose x. So that gives us our probability function for the binomial random variable, n choose x, p to the x, 1 minus p to the n minus x for x equals 0, 0 up to n. Next time, we'll see some examples of the binomial and also look at the relationship between the hypergeometric and the binomial. I hope you have a great time at the climate strike if you go. Otherwise, I hope you have a great time not being in class. Have a spectacular weekend, and I will see you on Monday when we'll continue with the binomial and hypergeometric. Have a great day.